Hello? Okay. Okay, so good afternoon. Let's get started. So welcome to today's Physics Club. I think it's my honor and pleasure to introducing today's speaker, Logan Wright. Logan got his PhD from Cornell University with Frank Weiss. He mostly working on ultra short pulse, high power fiber lasers. So one of his achievement at PhD is to demonstrate spatial temporal mode locking of pulses in many fiber modes. That is actually it is really a landmark in this field of multimodal nonlinear optics. He also had many contribution to this field. But then when he finished his PhD, he went to Stanford, worked with Professor Yoshi Yamamoto, and later returned to Cornell, working with Peter McMahon on optical neural network. In particular, I think he pioneered this method of using physics-aware training to train a physical system to act as a neural network. I think this has work has attracted a lot of interest. So we are very fortunate to have him join Yale about 2 years ago in applied physics. And today he's going to tell you about his work on training physical systems like neural networks.
All right, thanks, Hui. I've only been here for 2.5 years, which is just enough time to be dangerous, but not enough time to finish anything. So ordinarily what I would love to do is to give a talk where we sort of go through systematically one piece of work and sort of draw the whole thread through the whole thing. Unfortunately, that's not what I'm going to do today. I'm going to give you more of a vibe of what's going on, because we have a lot of work in progress. We haven't finished anything to the point where I can give a full hour-long talk about something. I will give you some teasers about what's going on, but my hope is that by the end you're going to kind of be able to describe what is the genre of this lab. So in a nutshell, what we do is kind of inspired by machine learning. And in machine learning, I'm assuming many of you have heard of it. If you haven't, it might be a good thing to read about. In machine learning, you sort of automate the process of software engineering by applying a computational optimization procedure to learn the weights or parameters of an algorithm that has sort of free parameters, typically the weights of a neural network, which I will describe. But what you do is you learn this sort of mathematical object, right? This function that has these fit parameters that you've tuned, and then you compile it using the normal way you'd compile software to an integrated digital electronic circuit, and then that gets run to do the calculation. And what my group is doing is sort of similar, but we sort of cut out the middleman in the sense that we're going directly from a desired function, and that, as you'll see, needn't be a computational function. It doesn't have to be performing some mathematical operation. It could be a physical function in the real world. And we're machine learning physical parameters, so fields and voltages and things that you can feel with your hands, to get a physical system that performs this desired function. So it's exactly the analog of machine learning in the physical world. But because it's in the physical world, there are things that you can do that are not possible when you're confined to this sort of digital space. So because this is a transitional talk, I want to acknowledge both the members of my postdoc group, which worked primarily with Peter McMahon, who was a new faculty at the time. Much of this work was sort of come up with Tatsuhiro Onodera, who was my partner through most of my postdoc period, as well as Martin Stein, who's now a postdoc in my laboratory at Yale. So this is the group as of 2025. So the number of parameters is very quickly growing. When I introduce deep learning, I think physicists often find it attractive when I describe it as just doing high-dimensional curve fitting. And I find that the older the physicist is, the more they appreciate that point of view. And it's accurate. That really what we're doing with machine learning, and deep learning is an example of that, is that we have some function, and we have fitting parameters, and we just want to adjust these parameters such that we get this function performing the desired input-output transformation on this input vector x. And a standard sort of application of this, the sort of canonical machine learning task, is to take an input that is an image. So this image of my dog, for example, right? This is a vector because each one of these pixels is an RGB pixel, so it has 3 numbers associated with it. So you can put this in a big long list, send that in as a vector to this function, and the output that we would want here is a classification or an estimate of the probability of the neural network saying what is the likelihood that this image contains a dog or a cat. And of course, this is not a useful task. Useful neural networks are doing other things, but this is an example of the types of things that we would like to learn. And if it's well trained, it's going to then take an image of a cat, and the output will be this vector 0, 1 with 100% probability of cat. So the deep in deep learning is not, as I initially assumed when I heard about it, some attempt to hype up the field as if it's deep thinking, but it actually comes from a more technical place, which is that the functional ansatz for deep learning is a multi-layer neural network. And that means that the network is designed such that the output of one trainable nonlinear function is fed in as the input to a subsequent trainable nonlinear function, and so on and so forth. So the form looks like this. It's a composition of functions, right, with the input of the next one being the output to the previous one. It turns out this is a very non-trivial guess. It turns out that for many functions that are of real-world relevance, that have hierarchical locality, this can be way more efficient at learning and approximating them than a generic function that doesn't have these layers. And you can sort of intuitively think about that as I can take this task and I can decompose it into a sequence of steps. So instead of having to look at this image and in one shot immediately know that it's a cat or dog, I can sort of start by identifying the edges, and then I can maybe try and come up with a function that will count the number of appendages and so on. I can break it down into simple tasks that collectively in sequence can perform this task. The learning in deep learning refers to the fact that you apply not human ingenuity, but a computational optimization procedure called machine learning, or supervised learning in this case. So you have labeled examples, so inputs that you have an associated output with. And initially, these parameters are completely untrained. That means they're randomly set, so it's not like I put in an image and it will give me the right answer. What I do is I iteratively, over many examples in which I know what the right answer is, I update these parameters, these weights, so that iteratively and over time, the neural network will get better and better and better and better at doing this. And then, once that is done, I can take that neural network, I can take those fixed parameters, and I can then apply it to new data, ideally data that was not in the training data set. And I can then produce an inference. I can predict or compute this function for some new input that I haven't previously seen. And that's sort of the deployment stage. That's when these things are intended to be useful. So in a slide, you start with a completely untrained, randomly initialized functional ansatz that has some at least some plausibility baked into it. You then apply this very intensive computational optimization procedure, which requires not only a lot of compute, but also a lot of data. And over many, many steps, you can get this to learn how to do this function that is implied by the data. And then finally, you fix the parameters and you deploy it. So this has, over the last decade or so, been more and more and more and more popular. And the reason for that is that people have found as you increase the size of these networks, as you increase the number of parameters and just the amount of data and compute that you throw at them, they actually continuously get better and better. So these are now by far the largest calculations that humans have ever done. And there are empirical scaling laws called neural scaling laws, which are actually found by physicists. No one understands exactly what their origin is, but these are empirical curves which predict the performance, so the number of errors, for example, of a trained neural network as a function of the amount of compute used in training, the number of parameters in the network, the data set size, and so on. And the punchline of this is that as you make these networks bigger and bigger, they seem to reliably get better and better and better. And although there's some certainty in that, most of how these networks behave is not well understood. This is not like the design of a computer where a human has really thought about how each module is going to be fit together and there's a set of rules for how these things are constructed. Neural networks are really grown. They're self-organized systems, and we don't necessarily understand their behavior once they have been trained. A good example of that appeared in 2020. This paper, Language Models Are Few-Shot Learners, which is the basis for the ChatGPTs and the clouds that we use now today, which found that as you increase the number of parameters in a particular kind of neural network trained on a particular kind of task, namely predicting the next word or token in a sequence of text, that eventually you can get to the point where there's an emergent transfer learning. And what that means is that the network can begin to very effectively do tasks that it wasn't trained on, right? So Hui asked me if I could, change the length and style of some paragraphs, right? ChatGPT was not trained on doing that task, but yet emergently it is able to do that task. And actually no one knows why. This is probably an opportunity, I would say, for physicists to provide insight into how these self-organized systems are working. So that's not what my group is doing. We're interested in the physics of neural networks, but that's not the main focus of the group. What we are interested in is going from controllable mathematical transformations that live inside a computer to physical systems that live in the real physical world. So you can think about this is some mathematical ansatz that has some tunable parameters, but you can think about your favorite physical system in sort of the same light. The initial conditions to that physical system you can think about as the input data, right? And that could be a field, for example, an initial field. The parameters of that physical system, for example, the geometry of the system, or the mass of the system, or the temperature, or internal parameters like the spring constants between different oscillators. These are knobs that we can control to change how this physical system evolves from its initial condition to some later point in time. Now, we could describe mathematically that effective analog computation by writing down the equations that describe the dynamics of that system, right? So physics provides an insight into what is the computation that this physical system is performing. But fundamentally, this is a physical process. It's not a mathematical process on a computer. It's a real analog physical thing. So an example is, which you can play with here if you like, is a network of coupled pendula, right? So here, the input data can be the initial angles, right? So all these pendula, you can set them to some initial angle, and that allows you to set up this initial condition vector. And you can tune how they're going to subsequently evolve by changing the strength of the spring constants that couple them together, or by applying fixed torque to each one of these pivot points. And then you can read out the result of this computation by measuring, at some time later, the angles of each one of these pendula. So that is a sort of classic physical system. And you can take that sort of physical system and construct a network of these transformations, right? You don't have to do just one physical system. You can take the output of one physical system and feed it subsequently into another one, just like in a deep neural network. So what a physical neural network is, it's a network of controllable physical transformations that we train using a computational optimization procedure to perform physical functions in a manner that is similar to how artificial neural networks are trained to perform mathematical functions. And this is not something where we don't, for instance, need to say, oh, well, there's a ReLU activation function in a transformer neural network, so we need to have a physical system that implements a ReLU activation function. We don't need to be that fine-grained about it. In fact, this analogy works quite well, even if you're really talking about a physical system like this, that only very approximately resembles what is going on in a standard artificial neural network. So coming back to this, I want to show you what you could do with a system like this. So these are the equations of motion for this network of coupled pendula. We're going to encode information and control the evolution just as I've described so far. And we can take an image. So this is an image of a fashion item, a pullover, apparently. And we're taking chunks of this image and feeding them in as vectors to 49 amplitudes of these oscillators. So we have 16 100 by 100 networks of coupled oscillators. And we feed these in as initial conditions along with some 51-dimensional vector that we can learn. And we take the output of these and then feed it into a much larger network. And we look at 10 of these oscillators, 10 of these pendula, and we measure at some time later what is the amplitude of those 10 pendula. And the idea is that, for example, the 10th of those pendulums will, if it is a high amplitude, encode a prediction that this is an ankle boot. And if it's the 9th, it would predict that it's a bag and so on, right? So we're reading out the physical results of the computation from the final amplitude of these 10 oscillators. Okay? I know it's complicated. Unfortunately, this is actually as simple as it gets. These neural networks are generally very complicated. They now routinely have trillions of parameters. But when we train this device, when we train this physical network, we can indeed get the functionality we are looking for. So here's a phase-space plot of the dynamics of the first 100 oscillators in this large network. You can see it's not linear. There's some nonlinearity involved here. And these are the dynamics of the readout oscillators. And for an example where the input image was a t-shirt, you can see that at some time, 0.5, where we've chosen to measure, the amplitude is high. So it's encoding a prediction that this image is probably a t-shirt. And we can train this identically to how we would train a deep neural network. So over steps, it gets better and better and better. And eventually, we get to a point where when we have an input that corresponds to one of these articles of clothing, we're most of the time getting it correct, right? So ideally, we would have this show that 100% every time a t-shirt would come in, we would always predict it to be a t-shirt. We're doing pretty good. It's not state of the art. This is not about to, no one at NVIDIA is sweating about this result, but it is surprisingly good for just a random network of springs. So in my postdoc at Cornell, I was sort of thinking about ways in which we can use physical systems to do computation. Is there a question?
To what extent is the nonlinearity of pendulums vital? I guess, does it matter if the pendulums are if they're springs?
It's not necessary that the physical system have nonlinearity. Here there is nonlinearity. So here we're not making a small angle approximation. This is a full Frenkel-Kontarova model here. But if you have a linear system, it can learn to do linear functions. It just couldn't learn to do nonlinear functions. So you do need nonlinearity in general to learn more complex functions. Does that answer your question? All right. And yes, please stop me. There's a material that I could get through, but there's not really a lot that I need to get through. So yes, we're examining many ways that we could use physical systems to perform computation, and we had some examples like this. And there was a moment where I was sitting in the basement of Clark Hall, which is the applied physics building at Cornell. Predictably, it's a very ugly building. It's kind of really not pleasant to be down there. There's not light like this. Tatsuhiro and I sort of turned to one another, and at the precise moment, we sort of said, like, how general is this? Is it possible that everything could be a neural network? And I said yes, because I'm somewhat careless. And Hiro said, well, that seems unlikely to be true. So we engaged on a quest for the next 2 years to see who was right, and it turns out I was right. That's not giving Hiro enough credit. He was also correct. His answer was that, yes, it can be, but most of them will be useless, which is in fact the case. So we constructed controllable physical systems. We had Martin Stein put a piece of aluminum. So this is a metal plate that he glued to a speaker. So now this is like a multi-mode mechanical oscillator that is driven like this. I made at home, this was during COVID, this very complicated analog electronic circuit. It's nonlinear. There's a transistor here embedded in an RLC oscillator. And then we have some other nonlinear optical system that I won't describe. And with networks of those physical systems, we were able to train them to do image classification. Again, none of these are impressive if you compare them to what is possible with state-of-the-art GPUs. But I can tell you without a shadow of a doubt that this is the most accurate image classification ever performed by an oscillating metal plate. So that's sort of evidence that we can do this quite generally. But I'm skipping this part, right? I'm just talking about this part. So how do we do the training?
Can I ask one more?
Go ahead.
How do you know whether these image classification problems at work are they linear or nonlinear?
They are nonlinear, and if we want to get really into the technical details of this, there's some cutoff. Depending on for this particular task, I think you can get 92% accuracy with a purely linear model, and anything above that, you need nonlinearity, right? So you can see here, I was working really hard to make sure that I got 93, because I knew that there would be referees who would going, bah, but 92 would show that it's linear. The 87% accuracy here is also an indicator that this system actually turned out to be linear. We didn't want it to be linear. Actually, we're really giving Martin a hard time. We're like, we want this to be a nonlinear oscillator, but he's a very good scientist and was like, no, this is just a linear system. And we said, it's a pretty good linear system. So the way that we initially planned to do this was using a method that is used in the field of physical inverse design. So Owen Miller at Yale in my department is one of the world leaders of this in photonics. And essentially what one does is you have a time-evolved physical system, for example, the propagation of light within some medium, and we compute somehow, typically using a method called the adjoint method, the gradients of the adjustable parameters with respect to some objective function. So this is, and then we update these parameters such that our design, the sort of the physical system that we're manipulating to try and serve some objective, gets better and better and better. It's actually not widely appreciated, but it's actually the exact same algorithm that is used to train neural networks. It's just sort of arrived at through different conclusions. So we wanted to use this. Now it turns out that this method doesn't work at all with most physical systems. And the reason is that your model is typically not an accurate representation of reality. Even tiny little differences can really add up. You can think about errors propagating not only from layer to layer of this, but propagating over many steps of this optimization. So a design that might work in simulation rarely works in experiment. So we did really want to get backpropagation to work, though. Backpropagation for performing gradient descent is overwhelmingly the algorithm that is used in deep learning. And the reason for that is that backpropagation can be implemented using a framework called autodifferentiation. And what autodiff allows you to do is essentially compute derivatives of functions analytically. And that means that rather than having to do gradient estimation by performing finite difference, where you would have to, if you have n parameters, you would have to perturb every single one of those n parameters. So that will scale as order n. If you can just analytically calculate the gradient, you can get the gradient in one shot. You don't have to do finite difference perturbations. So that means that backpropagation and methods like it are n times faster than gradient-free methods. And this is a big deal when you're talking about 1 trillion n. So we really wanted to get this to work. And the trick to getting it to work turned out to be really stupid. What we did is we just perform inference. So we evolve the physical system with our current set of parameters. And to compute the gradient, we just do what you do in inverse design. We have a simulation model, and we use that to analytically calculate the gradient. And so we have this hybrid process of the real physical system on the forward pass, and then we update the gradient with a model. And it turns out that this coupling between the world of reality, where you're actually measuring the objective function, and then using this model to predict the gradient, it turns out that that works well enough. And the intuition we eventually arrived at was that really what you're trying to do is sort of find a minimum of some very high dimensional landscape. And it isn't that big of a deal. Like when you start doing a research project, you usually make a lot of mistakes, but as long as you're generally going in the right direction, not as long as you're not going in the opposite direction, you're going to continue to make progress. So it turns out the gradients don't need to be that accurate in order for this to work. But since that initial paper, there have been many proposed methods for training physical systems beyond this original algorithm, including forward training and methods that use the physical system itself to perform the learning process. So they actually use the fact that the physical system exhibits time reversal symmetry to allow it to compute the gradient or the adjoint field itself. So you can do the whole learning process on the physical system. And if you're interested in this, we have a review paper that recently came out. This is probably the best introduction to this field that kind of surveys all these many, this now a growing zoo of algorithms for training physical systems. So what I want to talk about now is, so we have this capacity to train physical systems to do stuff, right? We can just like we would in machine learning, we don't really need to know a design. We can just sort of computationally brute force it. What can we do with that ability? So in machine learning, as we know it now, we're interested in learning vector-to-vector mathematical transformations using this process. But with physical neural networks, we're not constrained to digital data, so we can learn physical transformations, right? The input can be a physical object. It can be patterns of photons that are coming from you to my eyes, right? Or it could be, it could be a signal from deep in the universe, some microwave that is coming at you. It doesn't have to be digital. And that's the key for many of these applications. So an example of that is we can use an optical neural network, abbreviated optical processing unit here, to pre-process a photonic input prior to capturing it with a digital camera. So in a conventional machine vision system, you sort of have a camera, right, that is looking at a scene, and it captures a full image, right? And then that image is sent into a neural network, and that neural network will extract information of interest from that image, right? You might want to train a neural network to say, I'm going to extract all the text from an image. And many neural networks do this, especially neural networks that are being used to transcribe text into a digital format. But it's kind of wasteful if you think about it, because we don't really need all this information, right? We don't need a megapixel image with full color to give us two numbers. So what we can do instead is take those same photons and send them into an optical neural network. And that optical neural network can learn to extract the information we care about and put it into a compressed format. And then we take that compressed format, which is still a beam of light, and we send that compressed beam, now with fewer degrees of freedom, onto a smaller camera from which we can more easily extract that information. Now, there's at least three reasons why this might be interesting. One is that now this processing can be sensitive to aspects of the photon that are not normally accessible in a digital camera, right? In a digital camera, you have RGB, but with this, you could be sensitive to the continuous spectrum of light. You could be sensitive to the polarization or even the quantum properties, the noise, and even the entanglement of the light. The second thing is that as you reduce the number of pixels here that you need to use, this camera can begin to operate at much higher speed, right? Because it's generally limited by reading out all the data from these pixels. So we can go much faster. And my colleague, Tianyu Wang, has been developing a system to do this for doing image-based flow cytometry. So he can look at hundreds of thousands of cells that are flowing through a microfluidic tube, and he can do machine vision at 100,000 frames per second by doing optical neural network pre-computing. That being said, the reason that we started down this path is not to create front ends for machine vision systems and to machine learn physical sensors. It is that we had a more ambitious aspiration, namely we wanted to beat a GPU. And so you can do that. You can imagine putting digital to analog converters and analog to digital converters, and in the middle putting one of these programmable physical systems to act as an analog accelerator for doing deep learning calculations. And this can actually make a lot of sense. This is the architecture that is widely utilized now, or at least a version of it, in GPT models. This is a transformer with its multi-attention head and then the MLPs. And most of these operations are linear. They're linear algebra operations, matrix multiplications and matrix multiplications. So this is overwhelmingly the computational cost, is performing these linear algebra calculations. And that's really good news for doing computation with optics rather than with digital electronics. And I'm going to explain this a few different ways over the course of the next 25 minutes. But optics, linear optics, allows you to compute a matrix vector multiplication with a cost that scales only with the vector size rather than with the number of elements in the matrix. So if I were to perform a matrix vector multiplication on a digital computer, that's going to require order of n squared operations, right? One for, you can think about it, one for each multiplication and addition that is involved in each element of the matrix. But with an optical system, I can actually just pay the price of preparing the input vector. So I just prepare a beam of light that has that information encoded in it. And then to perform the matrix vector multiplication, all I need to do is send it through some specifically designed optical system. And that propagation of light is passive. It costs as much as this. So that part is free. And then I have to pay the price to measure those beams of light at the end. But that preparation and measurement only scales as n. So there is some point where optics can be more energy efficient than electronics. An example of this being implemented is the Stanford vector multiplier. And the way this works is you have an array of lasers here. And these display the input vector amplitudes. And then each one of these is spread out, kind of like a sausage, along a display. Right? So this one gets mapped along this column. This one gets mapped along this column. And what these pixels here are is they're attenuators. They can attenuate the light a little bit. So they can change the amount of photons that propagate through each one of these regions. And if you are taking a beam of light and you're multiplying it by some attenuation factor, that is a multiplication. Right? You're producing a multiplication of the initial amplitude with the attenuation. We then take these rows, and we have optics that focus these rows onto detectors that are arranged like this. And by simply summing up the current on those detectors, you've now performed a matrix vector multiplication. So this is not the only way to do it. In fact, it turns out that you can do it very ubiquitously in optics. But this allows you to literally take the mathematical operations and map them to a passive evolution of light through a device like this. So we, or Maxwell Anderson, who's a PhD student at Cornell, wanted to see whether this would actually matter for implementing large neural networks in realistic computers. So taking into account all the details that electrical and engineers and computer scientists normally get their pitchforks out about. So we really considered all the details, and Maxwell generated a plot like this, which at the time we were very excited about, and now I have to always apologize for, because it is very complicated. But this, to me, very beautiful plot, which shows the amount of computations required for the neural network on the x-axis, and the total energy per inference. So each time you use this neural network, how much energy does it expend? On here are points for many, many different existing models. And these lines show the energy scaling cost for an optoelectronic computer, so using optics to perform these linear algebra operations. And then up here are optimistic digital computers. And you see that the slope of these two lines on this log-log plot are different. And that's the punchline of the work, is that this scaling advantage is actually preserved when we consider the fine print. So as you make these neural networks larger and larger, the advantage of using optics to perform the computation gets larger and larger. In principle, for future models that are getting to the scale of hundreds of trillions of parameters, this could be a very non-trivial improvement. This could be tens of thousands or hundreds of thousands of times lower energy cost. So in my group, we are working on a technology to allow us to do computations with light, not in this sort of bulky apparatus like I showed you thus far, but by controlling the flow of light through a chip, right? So we want to be able to have something that could be millimeter size that could fit inside your smartphone or something like that. And the way that we're doing that is we're constructing a waveguide, a photonic system, in which light propagates in 2 dimensions, so it's confined in this y dimension. It evolves roughly by an equation here, which is called the paraxial wave equation. And we can control the propagation of light through this slab by controlling the distribution of refractive index inside that material. Now, if that doesn't appear familiar to you, it should. This is exactly the same as the Schrodinger equation, where we now have replaced z with t, and the refractive index is just the negative of the potential. So you can think about what we're doing is designing a time-varying potential to transform input eigenstates to a desired output eigenstates. We rely on 2 effects to make this work. One is the electro-optic effect. So in some materials, like lithium niobate, if you apply a voltage, a field, across the material, it will change the refractive index of that material. And these are used widely, for example, to modulate laser beams, to encode information on them so they can be transmitted through fibers across the sea of the Atlantic Ocean. The second effect that we rely on is photoconductivity. And that is when you shine, typically green light, it needs to be above the band gap of the material, onto a material, its resistance will drop. And this is really just because you're creating more carriers, so its conductivity is going up as you create these photocarriers. So combining these 2 effects allows us to fully program the refractive index distribution of a slab of photonic material. Maybe think just a little bit about how that might happen, and then I will spoil it. So the way that we do it is we use the photoconductor to act as an array, an infinite array, ideally, of electrodes. So by shining light on the top of this device, at every single pixel of the top of this device, that photoconductor allows us to control a potential, a DC electric potential. And by then putting that potential across a piece of electro-optic material, like lithium niobate, we can then get a refractive index modulation through this electro-optic effect. So the device we built looks like this. It has a lithium niobate waveguide. So this is where light will be confined. And this is also an electro-optic material. And on top of that, we place a thick film of a photoconductive material. And we have an electrode here on the top as well as the bottom. We apply a strong DC field across this device, so I put a big voltage here. And then we're going to shine light on the top of this device and also shine light through this device. And this light will be green, and this light will be in the infrared, right? Because we want to be able to generate photocarriers with this light and not with this light. In regions where the photoconductor is not illuminated, if you look at the circuit diagram for this circuit at that pixel, the photoconductor is going to be highly resistive. So the voltage drop is going to be primarily across the photoconductor, not across the waveguide. But in places where we shine light, that field is going to get switched to be across the waveguide. So now through the electro-optic effect, this spatially varying DC field is going to give rise to a spatially varying refractive index distribution, which allows us to control the optical potential in 2 dimensions, just by the pattern that we shine on the top of the device. So this is what it looks like in the laboratory. Light is coupled through this objective through the device, and then we're shining light on the top to control this refractive index distribution. So Mardenstein first described to me the merits of this approach with the following analogy. So you may or may not know that there's a quite emerging industry of making integrated photonic circuits, analogous to making electronic circuits, but instead of electrons, it's photons that are propagating through these circuit elements. This is something that's being developed, for example, by TSMC and NVIDIA for next generation GPUs. But here, the way that this works is you have to etch out. You have to sculpt away, remove material to make a fixed device. So it's kind of like sculpting but what we're doing is a lot fancier. It has the capacity to be reconfigured. So it's a little bit more like this, and that we can holographically control the circuit at will. So we set out to do machine learning with this device. So we're doing this image classification task. This is a downsampled version, so it's a coarse-grained version of that image. We take that 2-dimensional image, we unroll it into a 1D vector, and we send that as a beam of light into this chip. It then propagates through that waveguide, and we look at the output beam, and we look at these 10 different regions. And if, for example, the 9th region has the most energy in it, that will encode the prediction that this is a 9. And it turns out that's correct here, even though I know it kind of looks like a 4. So we apply backpropagation. We apply this physics-aware training algorithm to learn the refractive index distribution on the top such that we get the desired classification performance. So that's just exactly the same as you would do in conventional machine learning. And with that, we can get an all-optical system that can classify these handwritten digits with 86% accuracy. So if the image shows a 1 or a 2, it will get it right 86% of the time. So we were very pleased with this result. The people, again, at NVIDIA are not losing any sleep over this. This is very, very far from state-of-the-art. 86% is actually worse than you can do with a good linear digital model. So it's not even breaking the nonlinear barrier. And that's okay. This is a linear device. But I can say that at least at the time of putting on the archive, this is by far the largest on-chip optical computation that has ever been performed. And the reason for that is that the whole device is just parameters. The whole thing is trainable. So it's very dense in terms of the computation that we can perform. That being said, it's really kind of as fun as this experiment was to do, and as cool as this device is, there's a lot of sort of engineering that needs to be done to improve its performance. So it's not something, we're not building a startup company about this anytime soon. So in my group, Martin, Yuchi, and Jay are sort of working on the next generation of this device. We have a number of goals. The main goal is to really beat a GPU, which we think is somehow surprisingly possible. But we have many other aspirations. I don't think that we'll get all of them, but some of them, including, for example, building circuits that might be useful, for example, for quantum computing. So I promised that I would explain this optical energy scaling advantage in a couple different ways. And one way to understand it is actually from the quantum noise of light, which is ultimately what limits the accuracy of this computation. So we have an optical system like our waveguide, and we send in n modes that have some average number of photons n. And on average, the output signal-to-noise ratio, assuming there's no loss in the system, will be proportional to n times n. So it's going to be proportional to the total number of photons that come out here, square root. Why is that the signal-to-noise ratio? It's because the photon energy is quantized. So as we're performing a measurement of this light, if the light is very low intensity, the fact that it doesn't come in a continuous analog signal, but actually comes in finite photon-sized chunks, creates noise, right? This is called shot noise. So the fact that this is not a continuous smooth distribution, but it looks like one as you go to higher and higher photon numbers, is the origin of this quantum noise in these calculations. So the order n scaling advantage arises because if we just want to keep the signal-to-noise ratio fixed, we can reduce the number of photons that we allocate to each mode by 1 over n relative to the single mode case as we increase the size of the vector without losing accuracy in the output. And that's another perfectly isomorphic explanation for where this 1 over n scaling advantage comes from, that we're summing these n photons, and all we care about is this output vector. We don't actually care about the accuracy of these individual multiplications because we're not measuring them. So Jinchen Zhao in my group has been looking at this quantum limited accuracy and asking what would happen if we could go beyond it. How could we go beyond it? And his hunch is that we can utilize a process called squeezing, which allows us to take a Heisenberg-limited optical field and redistribute the noise within it. So we can't reduce the noise below the quantum limit, right? We still have to satisfy this uncertainty product, but we can make the noise go in places that we don't care about and reduce the noise in places that we do care about. So if we have a optical matrix vector multiplication, and we have input squeezed lights, input squeezed modes, and we care about some fraction of the outputs, Jinchen derived that we can get, with an optimal squeezing allocation, a boost of the signal-to-noise ratio that scales as the square root of the average number of photons in these modes times the ratio between the input dimension and the output dimension. And intuitively, what is going on here is as we increase the number of photons, that is allowing us to do more and more squeezing. We can increase the ratio that we break this circularity. We can, as we increase the photon number, we can make this more and more or less like a sausage. And this ratio of n over p is because essentially what we can do is we can say, well, we only care about these outputs, so we're going to put all the noise into these parts that we don't care about. We're not going to measure them, they're not important, and we can reduce the noise in these parts of the calculation that we do care about. So this leads to an improved scaling advantage of n to the minus 3 over 2, depending on the size of p. It also matters when you're talking about a deep computation, right? When you're talking about an analog computation over multiple steps, the noise is going to build up. As you do each one of these operations, error is going to propagate. This has been the downfall of analog computing for many decades. But what Jinchen has showed is that if we can optimize the squeezing, the distribution of noise within this analog computer, we can get a square root L signal-to-noise ratio advantage, where L is the depth of the network. And this translates to significantly different scaling laws. Right? I suggested before that one of the driving factors in the field of machine learning are these neural scaling laws, which predict the performance of neural networks as you train them larger and larger. What Jinchen has showed is that controlling quantum noise allows us to enhance those scaling laws. So I just want to give you one more example before moving on to conclusion of a last way that you can use a physical neural network, which is that you can use it to generate. You can use it as a manufacturing device. You can train a physical process to generate some physical output, some object that you're interested in. So Rudy Zhu and Hao Wei in my group are working on this. They are trying to design a time-varying optical field from an ultra-short laser pulse that will then interact with a molecule and will control aspects of this interaction. I'll give you an example just now. Currently, this is all in the computer. We're working on moving it into the laboratory. We recently got our laboratory finished. But the way that we describe this light-matter interaction involves just taking the electron, describing its Hamiltonian, and then describing the coupling between the electron and a light using the dipole moment. So the parameters that we're learning here is this time-varying electric field, which is perturbing this base Hamiltonian. Then we evolve using the Lindbaum master equation. The application that motivated this is deep tissue multiphoton microscopy, which you may have heard of. So this is an approach to doing volumetric imaging, potentially in deep tissue. And you shine a laser beam on the top of a sample, which could be like a mouse's brain, for example. And what you want is that only at the focus will you generate a fluorescent signal. So you're going to focus this light in, and right at the focus you're going to generate fluorescence. And why is it that only at the focus you generate fluorescence? It's because instead of exciting this molecule by having one photon that brings it to an excited state, you rely on the fact that you can excite it with two photons that team up. And this two-photon process, this multi-photon absorption process, only happens when the light is really intense. So it can only really happen at this focus. And this allows biologists to get images like this of three-dimensional structures within biological organisms. And this is increasingly becoming the state-of-the-art method for looking at three-dimensional biological behaviors in at least a few millimeters of tissue. So we set out to apply this PNN approach to designing a laser field that would interact with a rubidium atom and maximally excite fluorescence of this pathway. And what Rudy Zhu found is that if he applied this machine learning approach, he could get 30 times more efficient fluorescence. That is, he would get fluorescence 30 times more efficiently with a given amount of optical energy compared to what was long believed to be the state-of-the-art pulse shape. And when we go to a more complex molecule like coumarin here, this is a dye that is typically used in these experiments, we get an even larger advantage. So the question is, as we go from one atom to order of 10, what happens when we go to 100 or 1,000? Right? When we go to really big complex molecules like this, where you don't even see the atoms, can we get an even larger advantage? So we don't know yet. The science is yet to be done. But the hope is that this number will get to be really, really big, and then we could build laser imaging systems that would allow us to image, for example, an entire mouse's brain or even a monkey's brain or something like that. So more broadly, you could apply this approach to any sort of light-responsive physical process with any feature and functionality that you would like to achieve. And you can design the field in multiple dimensions as well. So one long-standing goal for this type of thing has been to control chemical reactions, right? So you have a big vat full of molecules, and you want to drive specific chemical reaction pathways. You can do that by exciting molecules into particular excited states, which make those reactions more probable, among other mechanisms. You could, of course, do the things that many in AMO are interested in. You can control, with more precision, the interaction between optical fields and atoms or collections of atoms. Or, what is increasingly attractive, you could use these fields to control the spatiotemporal dynamics of electrons or even plasmas, right? So you could maybe design an electric field that would create a plasma that has this smiling face. You could also perhaps use it to create a plasma that would drive nuclear fusion far more efficiently. So this is what I promised. I hope it was somewhat successful. As I said, this is a very we're very much in the midst of things. We're not at a point where there's a lot of clearly defined outcomes. So I think this is the main takeaway as far as what we're doing topically. But I want to just close with a comment that really what my lab is about. When you start as a professor, you sort of have this grand vision in mind for what is your research direction, right? And it's because everyone is constantly asking you, what is your research direction? But what I've learned over the first couple of years is that the research group is not a design system. It is much like a neural network. It is a self-organizing, growing system. So if you really want to know what's going on with the group, you can ask some of these people who are really coming up with the ideas and doing the work and generating this output that I don't know what it's going to be. So here's a summary. The team page on my website has a little description of what everybody's project is. So if you're interested in this stuff and you want to find somebody to talk to, you can go here. But thank you for inviting me. I'm glad to finally get a chance to talk in the physics department, and I'd be delighted if you have any questions or criticisms now.
Okay, thanks, Logan, for this fantastic talk. And any questions, comments? Yeah.
Yeah, when you do the on-chip optical computation, you shine some light onto the chip, and that's how you control the refractive index.
Yep.
To shape the light that's on the chip. How do you shape the light that you shine onto the chip? How do you get that spatial resolution?
Basically this. It's just we can just use a display. In fact, one of the reasons why this is an exciting kind of approach is that we could eventually replace that top part. That could literally be a CMOS backplane for one of these displays from a camera or from your phone. And that, of course, scales with Moore's law. The rest of it is very simple. So yeah, that's the long-term approach.
Yes.
So some of the tasks you talk about seem to be things that we need supervised learning. I know at MIS there are some algorithms you can use for unsupervised, but if you're doing supervised learning or any of it, how are you including a loss function into this? Like how are you in the back propagation aspect?
So first of all, we don't have to do just supervised learning, but it's an astute observation that we do in this work. What I showed you is all supervised learning. So what is the loss function? The loss function is the exact same loss function that we would use, for example, in conventional machine learning. It's how many times are you classifying the image correctly, right? Over the batch, that is over the images that you just sent in, what fraction of them did you get right is more or less what the objective function is. For a task like the optimization of the fluorophore efficiency, the objective function, the loss function, is literally just the minus of how much fluorescent signal we get per pulse. So that whatever the objective is, however you would mathematically define that, that's the objective, and then we backpropagate that through the simulation to get the parameters.
I guess I wonder more in terms of the physical setup. How is that? Where is that coming into play? I know there's a few different systems you described, and so it's probably different for each one of them.
So where is the loss function coming in? So we'll do an experiment, right? And we'll say measure how much fluorescent yield did we get, right? How many fluorescent photons did we get? That gives us some number that is measured, that goes onto a digital computer, and we say, okay, we take the minus of that number, and that's our objective function on the digital computer. And then now we backpropagate through the simulation model, which is also on the digital computer. That tells us what the parameters should be. And we take those parameters and we update the physical system, and then we run it again. And we keep doing that iteratively, where we measure the output, we compute the loss function of the output, and we backpropagate and update the parameters.
Thank you for a very interesting talk. So in the artificial neural network, there are different types of architectures, like convolutional layers, recurrent layers. I wonder, how do you classify the physical neural networks? Do you call different photon-driven, molecule-based architectures, or do you belong to the same category?
So I love this question. We are very much thinking about what are the architectures that are optimal for physical learning. right? Because you can arrange these physical systems, or you could choose physical systems that are arranged in different types of network topologies, for example. And it's not obvious what kind of network topology will be best. I will tell you that none of these things, other than a few examples, map straightforwardly to one of those things, right? Not all these are just a convolutional neural network, or not all of them are just a multi-layer perceptron. They're their own thing. There's some complex nonlinear function, usually, that doesn't isomorphically map to an existing neural network architecture. But what we're thinking about in my group right now is what are the physical neural network architectures that are optimal. My own hunch is that it should be a hierarchical modular network, and I think it might be something that needs to have a very stretched region of criticality, but that's just my hunch. So we don't know what the architectures are. There's no words to just explain them. That hasn't been defined yet. That's sort of part of the fun of doing this new thing, is that we get to be the ones to invent those architectures.
Just a quick follow-up. I wonder if you could take any maybe biologically inspired module and compact to see which physical system you best.
You could, and people are doing that. There's a large contingent of the community right now that is interested in these types of systems, not for building better computers, but because they want to actually use them as sort of model systems for understanding how biological systems work, right? This is, in a way, we're building complex analog systems that do some desired functionality. We're sort of reinventing biology, right? So I have colleagues, Arvind Murugan at University of Chicago is one, where, his entire point of view on this is that this is how we will understand biological functionalities, right? And it's using the process that you described, right? You kind of try and build up a PNN that is made of the modules that exist in a biological system, and then you optimize it and see what its functionality is.
You mentioned that the gradient descent part of the process is done electronically. I was just wondering if you thought there might be a physics-based approach.
Yes, that is one of the grand challenges of the field, is to build a self-learning physical neural network. There are some proposals for how to do that that rely on, for example, when you have a network of resistive, a resistive network, it will automatically find a configuration of currents through that resistive network that minimizes the dissipation. So that's like a natural physical optimization. And people have been trying to find ways that how can we take a physical optimization, so some optimization that a physical system wants to do, and how can we commandeer that to make it do the learning that we want to do? So Andrea Liu's group and Doug Durian's group at University of Pennsylvania have done a lot of work on this. So we're thinking actively about it. It is the big question.
When you talked about the squeeze state approach, it sounded like initially it might be desirable to have small uncertainty in X, but then you showed these cases where the squeeze states had their sort of narrowest direction, either angled along X and P in different orientation than X and P space. So I was wondering what is the significance of that, or it looked like maybe the orientation was changing in subsequent steps of the training. I wanted to understand that better.
Okay, so there's two answers to that. The easy one is that that's a cartoon and I just made it up, and I know Jin Chen was cringing while I had that image. The slightly more charitable answer to me is that what matters is not necessarily the noise in any one of these input modes, because ultimately where a lot of the magic comes from is the correlations between these different states, right? Because what we care about is usually not like what is the input of the first vector, right? What we're looking for is some piece of information that is correlated, right? Like whether an image shows a dog or not there's no one pixel that says that. It's some linear combination of pixels that best represents that. So what we're really trying to do is minimize the uncertainty in that linear combination that has the highest mutual information with the quantity that we're interested in. So that does give rise to sort of counterintuitive distributions of noise.
I have a question. Is it actually necessary that the final layer has to go from I guess I'm kind of wondering if the last layer could be in traditional digital computation one layer beforehand?
So that is not only a good thing to wonder about. In fact, I think it's, for machine learning, the best way of using these systems. There's a whole area of the literature called reservoir computing, physical reservoir computing, where that's all they do. They have some random physical system, and they just take the output. They use it as a feature generator, so they compute they calculate a bunch of quantities with that physical system, just random functions of the input, and then they have a linear layer on the computer. And we've even extended that. There's work that is happening now at Cornell where we put it into a neural network, and we can even do better. So yeah, building hybrid systems that have some digital parts and some analog parts, that's a really good approach. I think I wish people in my community were more excited about it, frankly.
Regarding the setup with the lithium iodate and the variant refractive index, you mentioned that some companies, I guess, work on making these photonic integrated circuits, but it's entirely fixed. So it's part of the idea that you could have this varying refractive index for the training, and I guess iterate many times on the design and find your model that you're happy with, and then you sort of bake it into the hardware and I guess take the spatial variation of the refractive index and then make many of the photonic integrated circuits with that fixed model in mind, similar to like FPGAs to ASICs? In short, yes. We might not need to use the physical system there. We could just design it in a computer. But yeah, there's a whole parallel effort in my group led by Jay Zhao, where we're interested in building physical computers where there's no trainable parameters. It's like a CD-ROM, like we just make a physical computer and it's all fixed. And the advantage of that is that you could easily have 1 trillion parameters, because you can go in the fab and have a device that has 1 trillion knobs. So yeah, and then of course everything is totally passive. So that is not necessarily the only approach, because most of the time for computation you want to have a programmable system, but there are settings where that kind of like now making a fixed device that implements that calculation, there are many settings where that's exciting, including for ChatGPT inference.
All right, so any more questions? Okay, so now let's thank Logan again.